Alright, so we did a quick review of inverse functions, but today what I want to look at is actually bringing this into calculus, looking at the inverse trig functions, taking the derivative of those inverse trig functions. Okay? Now, you can see the rules listed here, and I want to mention a couple of things about these rules before we start actually using them. But notice here the derivative of arc sine is u prime over the square root of 1 minus u squared. Notice we go ahead and we're just dealing with this, whether this is a regular x, then u prime would just be 1, or whether we have a function in here. You're taking the derivative, putting it on top, and then the square root of 1 minus u squared goes on the bottom.
That looks like the Pythagorean theorem, the denominator.
Oh, yeah, it looks like there might be something in there derived from the Pythagorean theorem or something. Now, notice here, though, that the derivative of arc sine and the derivative of arc cosine are nearly identical. In fact, they're just opposites. And the cool thing about this is that if you have the cofunctions, if you look at the cofunctions, sine, cosine, tangent, cotangent, secant, cosecant, they're all opposites of each other, okay? The other thing that's nice is if you remember when we did derivatives of trig functions, remember that cosine, cotangent, and cosecant, the ones that start with C, were always negative? Well, that applies here also when you have the arc functions. Arc cosine, arc cotangent, arc cosecant are all negatives. And the other three are all the positives. Okay? So really, if you memorize the one set, it's very easy to remember the other set, the other three. Yeah, Harrison?
For arc sine, why isn't that just u prime over 1 minus u? Because the square root of 1 is 1, and then the square root of u squared is u.
Mm-hmm.
You can do it.
Why not?
Because it's not like individual. It's like when you do the Pythagorean, you can't distribute the square root sign.
Yeah, it's just like in Pythagorean theorem. I mean, square root of a squared plus b squared isn't a plus b because it's addition, and here because it's subtraction. Okay, so all right. So arc sine derivative is u prime over square root of 1 minus u squared. Arc tangent is u prime over 1 plus u squared. Arc secant is u prime over the absolute value of u times the square root of u squared minus 1. And then, of course, these three are just the opposites of their cofunctions. All right? So let's actually work through a couple of these and practice using them. All right? So first of all, we have the arc sine of 2x. And, of course, here we're going to use this derivative formula. What is u in this case? 2x. So du is 2. And one other thing that you'll see occurs in all three of these is a u squared. So it might be useful for you to go ahead and write down what u squared is. What's u squared in this case? 4x squared. Good. 4x squared. So now, using our formula, it's u prime, which I wrote as du. I'm too used to doing integrals. U prime. Okay? So 2 over square root of 1 minus the u squared was a 4x squared. And there's our derivative. Okay? For arctangent of 3x. Of course, we're going to use this formula here. So again, u equals 3x. What's u prime? 3. And u squared is?
9x squared.
9x squared. Okay, so we plug it into our formula. It's u prime over 1 plus the u squared, which is 9x squared. Okay? Okay, let's try another arc sine one. Change colors here. So we're using this formula again. U in this case is
X to the
square root of x, or x to the 1/2. And u prime is
1/2
over
x to
2
the
to
negative
the
1/2.
square root.
yeah, and that is 1 over 2 square root of x. Good. And then what's u squared?
X.
Yeah, u squared is square root of x squared, so it's just x. Okay? So now we have our formula u prime, which is 1 over 2 root x, over 1 square root of 1 minus u squared. 1 minus u squared is 1 minus x. Okay? Now this one, it would be helpful to simplify. Okay? We have a 1 over 2 root x in the numerator, so we could just pull that 2 root x down to the denominator, and it's 2 root x times the square root of x minus 1. And you can actually combine those two radicals as well, so it could be 1 over 2 times the square root of x squared minus x. One over 2 square root of x squared minus x. Okay?
Mr. Dixon,
Yes.
how come you switched from the radical 1 minus x to x minus 1?
Oh, when you look at the wrong thing accidentally. Thanks.
Oh, okay. No,
Sorry. Yeah, I just got that backwards. Yeah, so this is, 1 minus x, and so that would make it x minus x squared there. Thank you. And then finally, our last example, arc secant of e to the 2x. Okay? So let's think through this one. U would equal what in this case?
2x.
E to the 2x. Yeah, everything inside that arc function is going to be the u. So it's e to the 2x. What is u prime?
2e to the 2x.
Yeah, 2e to the 2x. And then how about a u squared?
E to the 4.
Yeah, there we go. It's e to the 4x. So when you do 2x and then it's squared, you just multiply the exponent. So it's e to the 4x. Okay? So, using our formula, the derivative is u prime 2e to the 2x over absolute value of u, so it's absolute value of e to the 2x, times the square root of u squared, e to the 4x, minus 1. Okay? Now question, is e to the 2x ever negative?
Yes. No.
No. E is positive. No matter what power you raise it to, it's going to be positive. Okay? So, I can cancel out the e to the 2x with the e to the 2x. Okay? right here, I can cancel this out because this will never be negative. Okay? So that gives me my final answer, which is 2 over the square root of e to the 4x minus 1. Okay? Alright, any questions on using these rules? Okay, this is just a basic application of the rules, but I want to make sure everyone is understanding what we're doing here. Okay, we got it? Okay? Alright, so the last example I want to look at is actually one where initially it's relatively easy, but then we want to simplify it, and I want to simplify it quite a bit so that we can see kind of how these can be useful in finding antiderivatives of certain functions. If you remember, I told you, you know, we don't have the product rule or chain rule or whatever, but by logic or by taking derivatives, we've been able to find some antiderivatives, and they have whole books of these things, or pages and pages of these antiderivatives that people have found for various types of functions, okay? Now, we don't have to memorize all those, thankfully, but this is where those things can come from, all right? And you can imagine how before the advent of the calculator that could do integrals for us, how useful that would have been, okay? But let's take a look at this derivative here. The derivative of y equals arc sine of x plus x times the square root of 1 minus x squared. Okay, so we want to find dy dx. So what is the derivative of arc sine of x?
You find
1 over
x.
1 over the square root of 1 minus x squared.
Okay, do you guys agree with that?
Yeah.
What's u in this case?
X.
It's just x. So the derivative is 1. That's why it's 1 over. Okay? Alright, so that's the derivative of arc sine. And then how are we going to find the derivative of the second half of this thing?
Product rule.
Yeah, product rule. So 1 times square root of 1 minus x squared plus x times, what's the derivative of square root of 1 minus x squared?
1 over 2 times
1 minus x squared
x squared.
Good.
times negative 2x.
Times the negative 2x. You guys agree with that?
No, something's wrong.
Exponent, right? Yeah, it's
I did not.
negative,
Oh yeah, negative 1 half.
negative 1.
Yeah, there we go. We lost our exponent. So a half minus 1 is negative half. Okay, so we've got this. Now I'm going to simplify this a little bit. The 2 is going to cancel with the 1/2, so that's kind of nice. And that leaves us with a negative x squared over the square root of 1 minus x squared. The middle part is just the square root of 1 minus x squared. And the first part is 1 over the square root of 1 minus x squared. So now if I asked you to simplify this, what would you do?
Yeah, you can do
What?
Common denominator.
Do what?
Yeah.
Okay, we could add the ones that have a common denominator, or what were you saying?
The common denominator for all.
We could get a common denominator for all of them. Okay, and in this case, notice if I multiply this by square root of 1 minus x squared on the top and the bottom, okay, it actually will just undo this square root in the numerator. Okay, so notice I've got now a 1 plus 1 minus x squared minus an x squared, all with that common denominator of square root of 1 minus x squared. Okay? So now what do we do to simplify?
2 minus 2x squared. I mean 2 plus. Yeah, no, 2 minus 2x squared. How weird is that?
Okay? Anything else?
2. Oh, you have to take the thing out.
Okay, let's take the 2 out.
Oh, you have to like not have a radical on the denominator, or is it fine?
We don't typically care about leaving them in the denominator, but what could we do?
Square.
What do you mean?
Like,
You square to get rid of the radical.
yeah.
Put 1 half and then bring it up.
If it were an equation, well, we could multiply by a form of 1. There's actually something a little simpler we can do.
I feel like the
We
1
can
minus
just
x squared
simplify.
cancels out.
You feel like it should be able to cancel out. Well, you're feeling right, but I want to make sure you know why. Okay? This is 1 minus x squared to the half, right?
Oh, could you
So it should
subtract,
be
right?
like,
so then it's 2.
What, Logan?
Subtract the exponents.
Subtract exponents. That's the first. It's to the half power on the bottom. So it's 2 times 1 minus x to the half power.
This is squared.
Huh? X, yeah, squared. Or we could say 2 square root of 1 minus x squared. Okay? Now, as you can see here, what they have right here is, notice, this is an example of how we could get one of those rules, okay? So if I wanted to integrate 2 times the square root of 1 minus x squared, or let's say I wanted to integrate the square root of 1 minus x squared, I could multiply this by a 2 here and a half here, and then guess what the integral of this is? It's, come on. It's what we started with at the very beginning. Okay? We took the derivative of that to get there. Okay? If we take the integral of it, we'll get back to what we started with. Now, would there be a plus c here? Of course. There would be a plus c. But you can see how taking the derivative of something like this and simplifying it can help us see other antiderivative rules. Okay? Questions? Comments?
Do you have any way to solve to find out the integral from the antiderivative?
There's really not any way that we would just be able to look at, hey, the integral of square root of 1 minus x squared. There's no way we would be able to figure out that equaled that whole thing down there. So, but this is how it's interesting. Historically, integration and differentiation, were kind of developed simultaneously for different applications. So Leibniz did more with integration from what I remember. Newton was a little more with differentiation. But their ideas were very similar, And as they did derivatives and then found these nice answers, and they said, oh, well, I was trying to integrate something that looked like that a while ago, so here's an antiderivative. I don't have to use the trapezoid rule or something like that anymore. I can find an antiderivative and use my fundamental theorem of calculus. Okay, so that's how these rules and things have been developed over the years.
How do we find out the formula of the differentiation for the arc, sine, arc, cosine, this inverse function of the
Trigonometric functions.
trigonometric functions?
Honestly, I don't know how they were derived. We saw that square root of 1 minus x squared. It might have. It looks like it has something to do with the Pythagorean theorem in there somewhere, but I don't know how they were derived originally. It'd be interesting to look up though.